Today's lesson is lesson 4 of Unit 12, Conditional Probability. We'll be covering pages 418 to 420. It'd be helpful if you had a calculator just for some simple dividing and 2 or 3 colored pens. So our first exercise asks us to revisit a two-way frequency table we saw in the last lesson. In this study, 52 graduating seniors were surveyed as to their post-graduation plans, and the results were sorted by gender. Let the following letters stand for the following events. M is for male, F female, C going to college, and N not going to college. So overall we have 30 male, 22 female, for a total of 52, and 29 going to college, 23 not going to college. If a person was picked at random, find the probability that the person was a female. So the probability of a female is here. There are 22 female out of the total 52. So the probability of female is 22 over 52. The probability of going to college, probability of college, 29 going to college out of the total 52 surveyed. C, the probability that the person was going to college given they are female. And the notation is this vertical line segment. This stands for given. Going to college given they are female. We want to draw a Venn diagram below to help justify the ratio that you give as a probability. So given that they are female, well, there are 22 females. And how many females are going to college? Out of the 22 females, 13 are going to college. And that's really all we need. So the probability of going to college given that they are female would be, well, they're already female and there's 22 females, so that would be our denominator. And 13 are going to college. D, which is more likely that a person picked at random will be going to college given that they are male? So the probability of college given male, or that a person will be male given they are going to college. Okay, so the probability of college given male, well, how many, given that they are male, I go up, there are 30 males, so the denominator would be male, and how many males are going to college? Whoops, sorry, here we go. How many males are going to college? 16. Probability of male given going to college. Well, going to college, there are 29 that are going to college. I'm looking here, I'm only looking at this here. There are 29 going to college. That's our denominator. And then of those 29, how many are male? 16. Okay, now, which is more likely? These are really too close to judge. But let's take the calculator. 16 divided by 30 is 0.53 repeating, and 16 divided by 29 is approximately 0.55. So the probability of male given going to college is slightly more likely, but ever so slightly more likely. I would really say they're too close to judge. Exercise 2, in the generic Venn diagram shown to the right, each dot represents an equally likely outcome of the sample space. Some of these fall only in event A, some in event B, some in both events, and some in neither. Okay, consider the probability of A occurring given that B has occurred. Give a formula for this probability based on counting the number of elements in each set and their intersection. Okay, so their intersection is 4. 2, 4, inside here is 6, so that's a total of 10 for set A. And 2, 4, 6, 8, for a total of 12 for set B. The probability of A given B would be, well, our denominator would be the number, lowercase n for number, in set B, and the numerator would be the number in the intersection of A and B. And remember, this is our intersection. This is A and B for 12s. It's great when we can count the elements that lie in the events and their intersection, but sometimes we cannot. So here we have a relative frequency table. A survey was taken to examine the relationship between hair color and eye color. The table below shows the proportion of the people surveyed who fall into the category. Each person was picked at random. Find each of the following conditional probabilities. Show the calculations you use. So find the probability that the person picked had brown eyes given that they have blonde hair. Okay, so blonde hair, which is this, right? This is what we're looking at, blonde hair. And this is a total of 0.35. That would be the denominator. And of these having blonde hair, how many have brown eyes? 0.10. Which is approximately, grab the calculator, 0.10 divided by 0.35 is approximately 0.29 if I'm rounding to the nearest hundred. Find the probability that the person had red hair given they had green eyes. So if we're given they have green eyes, so we're looking at green eyes, which is here, right? A total of 0.25. That's our denominator. Red hair. So of these who have green eyes also have red hair is 0.15. And 0.15 divided by 0.25, 0.6. Formula for conditional probability. All right, first, probability of A given B means event A given event B. And the notation is this. Probability of A given B is called a conditional probability. In other words, event B already happened. Now what is the chance of event A? So in this exercise, we have a room is randomly selected in a downtown hotel. The probability that the room has a king-size bed is 0.62. The probability the room has a view of the town square, so a view is 0.43, and the probability it has a king-size bed and a view of the town square is 0.38. Let K be the event that the room has a king-size bed, and let B be the event the room has a view of the town square. What is the meaning of probability of K given B? So it's the probability of a room having a view also has a king-size bed. So given that we have a room that has a view, what's the probability it has a king-size bed? So use a hypothetical 1000 table to calculate the probability of king-size bed given view. All right, king-size bed was 0.62, so king-size bed here, total would be 620. Right? Take 0.62 and times it by 1,000. View of the town square is 0.43 times 1,000 would be 430. So view is 430. And king size and view is 0.38. King size and view 0.38 times 1,000, 380. All right, so this would be 1,000. Just filling in the cells, 70, bring me to 500, so 570, 380 plus 50 is 430, 380 and 40 will bring me to 420, so 240. 620 plus 380, 1,000, and let's see, this cell would be 330. So, probability of king-size bed given view. So we're given we've got a view, so that's 430. As a view is 430. Of those 430, 380 have a king-size bed. Now, there is a formula for calculating a conditional probability. The formula is the probability of A given B is equal to the probability of A and B divided by the probability of B. So using this formula, the probability of K given B would equal the probability of V is the denominator, the probability of K and V is the numerator. So this would equal probability of K and V, that's 380 over the total 1,000 divided by the probability of B is 430 over the total 1,000. And now there's two ways of thinking of this. This is a complex fraction, meaning we have fractions within a fraction. And since these denominator of the numerator and the denominator of denominator are the same, they can just divide out. Right? So these would just simply divide out, and we'll be left with 380 over 430. which is the same as we found above. Or, let me just note that, remember, if we are taking a fraction and dividing it by another fraction, dividing by a fraction is the same as multiplying by its reciprocal, right? So it could be times the reciprocal of 430 over 1,000, which would be 1,000 over 430. Those thousands divide out. So we still get our fraction 380 over 430. How does the probability you calculated using the formula compare to the probability calculated using the hypothetical 1,000 table? They're the same. Let me even go back to one more thing here. Even if here I had used the probability of K and V was 0.38, so even if I take that 0.38 over the probability of B was 0.43, this is the same, right? This is 38 over 43, and this reduces to 38 over 43. So, formula to remember, right? The probability of A given B is equal to the probability of A and B over the probability of B. Another formula. And thank you for your attention.